Okay. Hey everyone, I'm Audrey, and this is my partner Brendan Mooers. Today we're going to be presenting our paper titled Human-Robot Teaming for a Cooperative Game in a Shared Partially Observable Space. So I'm going to run through all the human factor sides of this project, and then I'm going to hand it over to Brendan so he can talk about his 2D gaming framework. So why are we doing this? Well, everyone wants an agent that works as a good teammate, but how do you decide what's a good teammate? And also, how do you get to that point? That's what we are trying to solve. So if we look at what the current problems are in human-robot teaming, they seem to revolve around information sharing and communication. So for instance, if perhaps you over-communicate information, you can cause overwhelmed cognitive loads, but if you undershare or share incorrect information, you can cause a teammate to misunderstand another teammate's intentions and limitations. And if problems like these persist, they can cause bigger problems down the road. These include, reducing trust among teammates, causing uncooperative behaviors, reduced task efficiency, and ultimately compromising the safety of the team. So how are we going to approach solving some of these problems? Well, Brendan's designed a 2D grid world representation of a simplified search and rescue task. So simplified meaning that we are just going to focus on the search part right now, and later on we'll add the rescue part into later studies. So by reducing our environment and eliminating confounding factors, we can focus on what's important, and that is improving the understanding and sharing of information while maintaining balanced cognitive loads, accurate situation awareness, and multi-directional reliance among teammates. So to help us, we've created a shared meta model that is basically modeling these humans and robots working together to perform multi-objective tasks. So on the left side in the green, that's modeling the AI agent. The right side blue is modeling the human. And then the orange in the middle is basically the shared space and what's in common. So for instance, the arbitration module in the middle is going to handle all the dispute resolution. So this model is designed for cognitively intelligent systems that can allocate tasks and roles to teammates, can provide path planning, share vital information, and collaborate effectively with a human teammate. But what makes this model unique is that it can scale to fit multiple heterogeneous systems, robots of varying levels of autonomy, and also a variety of team configurations. So unmanned ground vehicles, aerial vehicles, underwater vehicles, etc. In designing our shared meta model, we've identified four main requirements for improved collaboration. These include, understanding an agent's intent, capabilities, and limitations, defining information required for informed decision-making, maintaining reliance among all agents, and also enabling the transparency and explainability of all the agents. And as a result, we kind of expect to see an increase in knowledge and understanding, an increase in robot independence, a decrease in human interference with the robot, and also improved task performance and efficiency. Because we're at the beginning of our research and validating and testing our model, we are focusing on how trust, performance, and information sharing affect each other, as well as cognitive load and situation awareness. We're also interested in studying how a human user trusts a robot agent, how that trust changes after successful or failed missions. So here I'm referring to trust refers to whether a human feels they can rely on a robot teammate and the information it shares. But in later studies, we're going to move away from trust because it's just such an abstract concept. We're going to instead focus on calibrating reliance. So the upcoming study that we have, you see the teaming factors we're interested on the left and the ways we're going to measure them on the right. For instance, performance and efficiency are going to be calculated from gaming metrics that are action metrics that are going to be collected from the game. We're also going to look at general trust in all autonomous agents in the beginning of the study, and then before each trial begins, we're going to assess trust based on the robot agent or robot teammate that they're assigned to. We're also going to use a dual test paradigm with real-time Saget probes to help us understand cognitive load and situation awareness of a user while performing the search task in the 2D grid world. So at this point in the presentation, we're done with human factors, and I'm going to hand it off to Brendan.
Turn this off real quick. All right. Thank you, Audrey. So yeah, I'm going to go through the actual game we designed here. Um, so Audrey touched on this a moment ago. So why did we choose a grid world? We want a very controlled environment versus a real world or a 3D simulation. This allows us to reduce those confounding factors that you might find when running experiments in those spaces. And we can easily run a large number of human experiments by keeping it in this simplified 2D space. We're also able to, by not doing a physical experiment, we're able to capture situational awareness through these questions that appear throughout the game. It also gives us a simplified representation of the world and allows us to further abstract agent behavior in this 2D space. We have three different views of the same map that are represented by these 2D arrays. There's the truth view, which is the actual representation of the map. The human view, which is initially empty, and it's populated by the truth view as the player explores the area. And then the agent view, which is also initially empty, but it gets populated by the truth view with imperfect accuracy as it flies through the area. In these two pictures here, that would be the truth view. And then over here, you can see the brightened squares being the human view, and the dim squares being what the agent has reported to be true. In our paper, we talk about two different types of agents. Agent 1 is your basic eye in the sky agent. So this is just a simple drone with limited to no autonomy, comparable to what's used in the field today. Just has some low-level control, sensing, and object detection. So just essentially giving a map of the surrounding area as the human tries to complete the task. And then Agent 2 is a path planner. So this agent has the same capabilities as Agent 1, but additionally, it recommends a path from the human to the goal. So this is meant to represent a real-world agent that has some level of decision-making, i.e. a teammate instead of just a tool. And it's worth noting we're not considering a black box deep learning agent at this point. We want these initial experiments, at least, to be explainable. So I'm going to go ahead and step you through the interface here. Up at the top, number 1 there, that's the player that's the human character that the player is controlling. Down there at the bottom is the goal with the drone hovering over it. Over on the right here, we display the status of the drone. So whatever the drone's current activity is, the player's status, which is just the last activity that the player has done, which they just explored a square. And then we also track the energy in the drone battery. The energy is the stamina of the human character, which gets drained as they explore the map. And the drone battery drains over time, and it gets drained further as the player makes use of commanding the drone around, which I'll talk about here in a moment. Below that, just the grid key, just to remind the player of what each grid represents. You can see the green grassy terrain costs 1 energy. The sandy brown terrain costs 4 energy to move through. These are the buttons that the player uses to interface with the game. So they can plan a path, which allows them to click on, draw a path up to 5 squares long and commit that to the human character to have them move manually through it. They are able to command the drone, which takes a significant portion of the drone battery, but allows them to reinvestigate an area and populate it with the truth view. And they can also just click that follow drone path button, and they'll follow that yellow line that the drone recommended to them. Yeah, and below that, that's where the questions appear intermittently throughout the experiment to measure situational awareness of the player. Here's another close-up just on the player's perspective. So like I was saying before, the bright squares are the human view, so they're accurate to the ground truth. The dim squares are what the agent has told the players there, so that there is some level of inaccuracy there. And the yellow line is where the agent is recommending to go based on its limited perspective of the world. And here, the player is plotting a course, ignoring that line and going to the left of this obstacle instead of circumventing it around. So when we were designing these maps, we we have to balance it between not being too simple and deterministic and not being so uncontrolled and impossible to understand that we don't get much information or much good data from these experiments. So we split these maps up into easy, medium, and hard difficulties. I'm not going to go through every single step here, but you can see it just ranges from errors being more impactful, backtracking being more prohibitive. So an error may be much more costly in a hard map versus an easy map. And generally, on an easy map, you should be able to reach the target without making much use of commanding the drone manually. On the hard map, you're going to have to really interact with the drone in order to reach the goal without running out of energy. Here's an example of what we would consider an easy map, the player being here and there's a goal. The red line is an existing obstacle that the drone did not see. The dotted line is a non-existent obstacle that the drone thought it saw. So in this case, the drone initially recommends moving around this entire obstacle, but as the player moves along this way, they can pretty easily see there's a gap in the wall. They can take a shortcut here, and from there they can move up here and reach the goal. So the errors here, they don't really cost too much for the experiment, but it does show the player that there is a possibility of the drone giving them some incorrect information. And then medium map gets a little bit more complicated. We have I'm introducing the orange rectangle here to represent the difficult terrain that the drone wants to avoid generally. So at this point here, the player can either go to the right, where the drone missed this wall, so they'll end up having to backtrack and cost some amount of energy to eventually make it to the goal. And then hard map, it definitely gets a bit more complicated, so I'm not going to step through every square here. The important thing is, if we were just following the drone blindly, you would end up in this corridor here, and this having to backtrack all the way through the map at this point would probably result in a failure state. So this is an example map that we used in the paper to represent a hard environment. I've highlighted a couple key areas here where the drone made some kind of mistake. The player starts up in this corner and the goal is down there. So this is the truth view that's not visible to the player, but you can see there's a couple areas like at A where the opening is actually on the left side. B, there's an opening here that, or there's an obstacle there that the agent did not see, and that's why it's pathing down this way. And then C and D, there's a couple more time saves that the player could take advantage of. So this is an example of what we'd call like a naive player going through the game on that same map. So this player is going to trust what the drone is telling them at every step. They're just clicking the follow drone path button at every time. And you can see those situational awareness questions popping up intermittently throughout the experiment. So they hit a wall there. The magenta outline just represents an area where the agent and the human's view did not match, just to let the player know that there's some kind of disconnect there. So they're going to keep following the drone path, and I'm not going to play the entire thing, but the spoiler alert, it runs out of energy at the end. It doesn't make it all the way through just by blindly following the drone. Here's an example of a more cautious player that takes advantage of sending the drone to reinvestigate some areas that the player finds suspicious. So first thing they'll do is at this fork here, they'll command the drone to reinvestigate that corridor. The drone's moving out to check it out, populates it with the truth view, and then from there they assume, well, maybe I can check the other path down, and that happens to be open. So this player will go through commanding the drone. It makes it to the goal eventually. These games are not deterministic, so it doesn't make it in the most optimal way, but they do save a decent amount of time by commanding the drone and altering their path based on that. How am I out of time? Okay. Yeah, so in conclusion, we presented this meta model with a grid world interface meant to evaluate those metrics. We present two different agent types, and varying map difficulties to use in these experiments. And we just kind of laid out our theoretical framework and our expectations going forward. This coming month, we plan on doing a pilot study of this game and then refining the game based on the information we learned from that study. And then following that, we'll be doing a full-scale study. And then future improvements, our main focuses are going to be iterating on the agent, so more strict definitions to differentiate the agents, and then eventually more advanced agents. And then finally to formalize the meta model and all of its components. And we're happy to take any questions.